So now we are going to start the study the principle of superposition, and that basically tells you what happens when two waves get to when two waves come together at the same point and at the same time. So the principle of superposition basically says that the net displacement the net displacement is equal to the sum of the displacements of each wave that is coming at the same time. When two or more waves are simultaneously present at a single point in space, basically same point at same time, the displacement of the medium, the net displacement at that point, is the sum of the displacement due to each individual wave. So let's see what that means. Say we have a wave here, a pulse that is traveling to the right, and one that is traveling to the left at the same speed. After 2 seconds, then this guy is going to be here at 4, and this guy is going to be here at 2. So what is the net displacement? Well, it's the addition of this plus this, right? And that gives you this wave here. After 3 seconds, then this guy is going to have moved a little bit more, and and the other one would have moved to the left. So you would have this here, and the net displacement is this blue line here. And then after 4 seconds, they have gone past each other, so the net displacement is 0 right there. So let's look at a question here. You have two wave pulses on a string. They approach each other with at 1 meter per second. So how does the net displacement look like at t equals 3 seconds? Take a minute. Well, at 3 equals 3 seconds, this guy, this one is going to be right here. This one is also going to be right here. And when you add these two together, you get this blue line here. So now you have this situation where you have these two pulses. They are again traveling at 1 meter per second, one to the right, the other one to the left. So how does it look at t equals 3 seconds? Take a minute. And this is the right answer right here. So this one, you would have this one here, right? This one would have moved to right here. This one would be here, and this one would be right here. So when you add the two, you get this there. So one phenomenon that is a consequence of superpositions is standing waves. And a standing wave happens when you have waves of the same frequency, wavelength, and amplitude that are traveling in opposite directions. And I'm going to show you what that means by a little demonstration here. So we have here a standing wave that I'm going to produce. So the standing wave now is traveling to the right, and so it's just traveling to the right, and then this end here, this is a string, and this end is fixed. So when this wave reaches this point, there's going to be a wave reflected that has the same amplitude and same frequency, but it's going to be traveling in the other opposite direction. And those two are going to add each other to produce a net displacement. So now it is starting to be reflected. So the blue wave here, this blue line is the reflected wave. The red line is the incident wave, the wave coming to the right. So you have the blue, the red, and the blue. And now this black line here, that is your net displacement. That is what happens that is what you get when you add the blue and the red. And notice one property of this black line. It has these points here that never move. These are called the nodes. Those are the nodes of your standing wave. And the maximums are always at the same location. These are called antinodes. Those are the antinodes of your standing wave. Okay, so that's a standing wave. We know what it is now. So And this is a similar picture to what we have. So the red wave is traveling to the right. That's like the right wave that we have. The green wave, in this case, is traveling to the left. When you superimpose the red and the green, you get the blue line, which is always going to have these points here, these points which are called the nodes, right? So these points, at these points, the blue line has the same position. It never moves. It is the same. Well, if I had drawn this straight, so this point here and this point here and this point here, those are the nodes. And your antinodes are this one here. So you can see that it's always the same. So this is a picture of a standing wave, and then what we can do is if we have a standing wave and we know the locations of the nodes or the antinodes, we can use that to figure out the wavelength, right? Because well, the distance from here to here is just half a wavelength. So we can measure that, or the distance from here to here is just half a wavelength, and we can measure that. And these guys never move. They are always in the same place. So what happens to the intensity? Well, the intensity of a standing wave would have this property. It has a maximum here at the antinode and a minimum at the nodes. So here the intensity is 0 and here the intensity is maximum. And the difference between this point and this point is half a wavelength. The difference between the node and the antinode is 1/4 of a wavelength. So this is half a wavelength. Here we have two wavelengths. This is one wavelength and this is another wavelength here. Okay, what is the wavelength of this standing wave? Take a minute to answer. And the answer is 1, right? Because you go from here, say, one node, two nodes, and then this is from, let's say, from this antinode, which is 0.5, to this, it is half a wavelength. So 0.5 is half a wavelength, therefore the wavelength has to be 1 meter. Okay, thank you.